Okay, number 15, we're given the equation, which we, okay. So I just need to balance. Okay, I have a 2 and a 3, so I'm just going to swap those to make them balance. And that's it. Okay, so if I have 28 grams of nitrogen and 25 grams of hydrogen, we want to know which is the limiting reactant. So we're going to compare the two. So I'm going to start with 28 grams of nitrogen and do a multimole ratio to hydrogen. But before I can do that, I have to change the grams to moles. So the molar mass of nitrogen is 28 per 1 mole. Okay, now I have moles, so I can do my multimole ratio. So it's just a 1 to 3. So 1 mole of nitrogen to 3 moles of hydrogen. Okay, now I gotta go back to grams. So I'm gonna go to grams of hydrogen. So 2 grams of hydrogen per 1 mole. And that gives me 6 grams of hydrogen. So I need 6 grams of hydrogen to completely react with 28 grams of nitrogen. Well, I have 25, so I have plenty. So that means nitrogen is my limiting reactant. So I'm going to start with my nitrogen, and we're going to calculate how much ammonia is going to be produced. So again, I'm going to go from grams to moles so I can do my multimole ratio. So I'm going to use the same step here. Grams of nitrogen cancel. Now I'm going to do a multimole ratio from nitrogen to ammonia. So it's a 1 to 2. And then back to grams. So ammonia is 17 grams molar mass. Okay, and that gives me 34 grams of ammonia were produced. Okay, so if I did found how much ammonia is produced using hydrogen, it would give me way too much because it is in excess. Okay, number 15, we have silicon plus N2, putting those positives so close, and then Si3 and 4. So to balance that, we just need a 3 in front of silicon and a 2 in front of nitrogen. Okay, so it says we have 602 grams of silicon, 494 grams of nitrogen, and we want to figure out what the limiting reactant is first before we figure out how much product is produced. So we're just going to compare the reactants. So I'm going to do a multimole ratio between the two, but I have to change the moles first. So I'm going to use the molar mass of silicon, which is 28.09. Okay, then I do my multimole ratio. It's a 3 to 2, so 3 moles to 2 moles. And then back to grams for nitrogen, which is 28 grams per 1 mole. Okay, so that tells me I need 400 grams of nitrogen. Okay, I need 400 grams, but I have 494. So I have plenty. Okay, so nitrogen is going to be my excess. Silicon is going to be my limiting reactant. So now I'm going to go from silicon to our product to figure out how much was produced. So we need to start with 602 grams. I'm going to do a multimole ratio, but I've got to get the moles first. So 1 mole silicon, 28.09 grams. Grams cancels. Now I can do my multimole ratio. It's a 3 to 1. So 3 moles to 1 mole. So moles cancel. And then back to grams, and the molar mass of trisilicon tetranitride is 140.27 grams per 1 mole. Moles cancel, and that gives me 1,200 grams of trisilicon tetranitride. And I think in the answer I put 1.002 10 to the third, same thing. And then the last question says how much excess is left over. Well, we saw we only need 400 grams of nitrogen to react, and we had 494. So we just subtract the two, 494 minus 400, and we had 94 grams of nitrogen that was left unreacted. Oh, I put, this is 16, sorry. Okay, now 17. Okay, 17. We're given a balanced, or no, it's not balanced, but to balance it, we need a 4, a 9, 3, and 8. So there's our balanced equation. So it says if 25.4 grams of aluminum oxide react with 10.2 grams, so 25.4 grams react with 10.2 grams iron, what is the limiting reactant? So again, we're going to compare reactants here. We want to do a multiple ratio, but before we can do that, we need to change this to moles. So the molar mass is 101.96 grams for aluminum oxide per 1 mole. Okay, then we do our multiple ratio, 4 to 9, so 4 moles of aluminum oxide, 9 moles of iron. Okay, and then we're going to go back to grams, and molar mass of iron is 55.85. 1 mole. Okay, so that gives us 31.3 grams of iron are needed to react completely with my 25.45 grams of aluminum oxide. So I need 31.3, but I only have 10.2, so this is my limiting. So iron's limiting, aluminum oxide is excess. Okay, so now that I know my limiting, I'm going to start with that. And it says how many moles of aluminum are produced. So I'm going to go from iron to aluminum, but it's only asking for moles of aluminum. So I just need to change this from grams to moles, do my mole-to-mole ratio, and then I'm done. Okay, so 55.85 is the molar mass of iron. So that cancels, and then we do a mole-to-mole ratio 9 to 8, so 9 moles iron, 8 moles of aluminum. And again, it's asking for moles of aluminum, so I don't want to go back to grams. I just want to finish it there. And I get 0.162 moles of aluminum. Okay, then the next one says determine the number of grams of iron, iron oxide. So we have, again, we're going to start with our limiting reactant. And we need to change to moles so we can get to the multiple ratio. Do the same thing here. Okay, now we can do our multiple ratio. So it's 9 to 3. So 9 moles to 3 moles. And here we do want grams, so we need the molar mass of our iron oxide, which is 231.55 grams per 1 mole. Moles cancel. And that gives me 14.1 grams of our iron oxide. Okay, last one says determine the number of grams of excess reagent left over in the reaction. So we know this is excess, but we never, aluminum oxide is excess, but we never calculated how much we needed to completely react with iron. So we've got to do that. So we're going to start with our 10.2 grams of iron, do a multiple ratio to aluminum oxide. So we've got to change to moles first. Okay, now we can do our multiple ratio, so it's just a 9:4. So 9 moles of iron, 4 moles of aluminum oxide. Okay, back to grams. 101.96 is the molar mass. Okay, so we're gonna get 8.28 grams of aluminum oxide are needed to completely react with my 10.2 grams. So it's tell us that we have 25.4 grams total of aluminum oxide, and I'm using up 8.28 grams of aluminum oxide in the reaction. So what's left over is 17.12 grams of aluminum oxide. So this is our excess. Excess that was left unreacted. Okay, now number 18. Number 18. If we're given a balanced equation. Okay. And it says if 8.78 grams of the As2O3 arsenic 3 oxide is used in the reaction, 5.33 grams of arsenic is produced. What is the percent yield? So they give us the actual, the 5.33 grams is the actual, but we have to find the theoretical, which is fine because they tell us just how much arsenic 3 oxide we have. They don't even mention carbon, so we don't have to find the limiting reactant. We can just start with our 8.87. And we're going to do a multiple ratio to arsenic, but we've got to change this to moles first. So the molar mass here is 197.84 per 1 mole. Okay, then we can do our multiple ratio, so it's 2 moles to 4 moles. And then back to grams. Molar mass is 74.92 for arsenic per 1 mole. Okay, so we get 6.72 grams of arsenic. So this is our theoretical yield. Okay, so they've given us our actual. Now all we have to do is take our actual 5.33 divided by our theoretical 6.72, multiply that by 100, and our percent yield is 79.3%. Okay, 19. So we have a balanced equation. Okay, there's our balanced equation. And we have 40 grams of sodium sulfate reacting with 25 grams of iron 3 phosphate, and it says 18 grams of sodium phosphate are produced for 18.5. And it wants to know what the percent yield is. Okay, so again, we have to figure out what is the theoretical yield, because this right here is the actual yield. Okay, so we've got to compare the reactants and figure out which is the limiting reactant. So I'm going to start with my 40 grams of sodium sulfate and go to iron 3 phosphate. So sodium sulfate is 142.07 per 1 mole. grams cancel. Now I can do my multiple ratio, so it's a 3 to 2. 2 moles. Okay, and then back to grams. Molar mass of iron 3 phosphate is 150.82 grams per 1 mole. And that gives us 28.31 grams of iron 3 phosphate are needed to completely react with our 40 grams of sodium sulfate. So we need 28.31 grams, we only have 25, so this is our limiting reactant. This is excess. So now we can start with our 25 grams and find our theoretical yield of sodium phosphate. Okay, so our molar mass is 150.82. Per 1 mole. Okay, and then our ratio is 2 to 2. So really it's a 1 to 1. Okay, and then back to grams. 163.97 grams of sodium phosphate per 1 mole. So that gives me 27.18 grams of sodium phosphate. Oh, sorry. 27.18 grams of sodium phosphate are produced. So this is my theoretical yield. I have my actual yield right here. So I'm just going to divide the two. So 18.5 grams divided by my 27.18 grams times 100 gives me 68.1% for my percent yield. Okay, last one, number 20. Okay, so we have a balanced equation, 2O3, 3H2, 2AL, 3H2O. Okay, so it says we get an 85% yield. How much aluminum will produce from reacting 700 kilograms of aluminum oxide to produce aluminum? Okay, so first of all, we have 700.0 kilograms of aluminum. We want to work with grams, so we can use our molar mass. So we've got to change that. So I guess I can do it like this. So 1 kilogram, 1,000 grams gives me 710 to the third grams. That's not really the right way. So you put 710 to the fifth. 7.00 times 10 to the fifth. Sorry. Okay, so that's grams of aluminum. Okay, now we can take that and it's saying that's how much was produced. So we want to figure out, the whole goal here is to figure out how much actual yield we have based on oh, I'm sorry, this is aluminum oxide. I was wondering. Okay. So we have percent yield, we can calculate theoretical yield, and then we'll solve for actual yield. Okay, so remember, percent yield is equal to actual divided by theoretical. So we can solve for that. They give us this, so we're gonna, since we have 2 out of the 3, we can solve for the actual after we calculate theoretical. Okay, so we have our grams of aluminum oxide. We're going to figure out how much of the aluminum is produced. So we're going to do a mole-to-mole ratio. Before we can do that, we've got to change to moles. So aluminum oxide is 101.96 grams per 1 mole. Okay, then our mole-to-mole ratio, 1 to 2. Okay, back to grams. Aluminum is 26.98 grams per 1 mole. Okay, so that gives us 3.7 times 10 to the 5th grams of aluminum. Okay, so the question says, that's okay. Well, we're going to change it to kilograms. So to do that, let me just keep doing that. Divide by 1,000. So that gives us 370 kilograms of aluminum. So that's our theoretical yield. Okay, that's our theoretical yield. So now we've got our percent yield. It's 85%. Okay, we're solving for the actual. We have our theoretical, and we multiply everything by 100. Okay, so I move 100 over, it becomes 0.85, because our goal here is to get x by itself. And then I'm gonna, since it's divided here, I'm gonna multiply by 370. So x is equal to 314.5 kilograms. So 314.5 kilograms is the actual yield of the experiment.